In Chapter 4, we use the method of undetermined coefficients to obtain a particular solution to a non-homogeneous linear second-order constant coefficient equation given by L of y equals AD squared plus BD plus C of y is equal to f of x, where f of x had a particular form, a polynomial function, an exponential function, a sine or cosine function, or a product of any of these. Why does this method work for these types of functions? In this section, we will answer this question by examining so-called annihilators. The definition of an annihilator is given here. A linear differential operator A is said to annihilate a function f if a of f of x is equal to 0 for all x. That is, A annihilates f if f is a solution to the homogeneous linear differential equation a of f of x equals 0 on the interval from negative infinity to infinity. So let's do an example where we try to find a differential operator that annihilates f of x equals e to the power 3x. So what we need to keep in mind here is that we're going to take a look at f prime of x. That's e to the power 3x times the derivative of 3x. So that actually gives us 3e to the power 3x. And another way of writing that is 3 times f of x. So that means that f prime of x minus 3 times f of x is equal to 0. And in operator notation, we can write that as d of f of x minus 3 times f of x equals 0, and we can combine that as follows: d minus 3 acting on f of x equals 0. So that means that our annihilator for this function is a equals d minus 3, because that makes this equal to 0 on the entire real line. Now, note that in the previous section, we saw that the linearly independent solutions to d minus 3 to the power 4 acting on y equals 0 are given by, remember what we needed to do there? We basically looked at the auxiliary equation, set that equal to 0, and that gave us r equals 3 with multiplicity 4. And so the solutions were given by y1 of x equals e to the power 3x. That's that r. And then y2 of x equals x e to the power 3x. And then y2 of, or y3 of x gave us x squared e to the power 3x, and then y to the power 4, or sorry, y of 4 of x, y4 of x equals x cubed e to the power 3x. So in other words, what we see is that d minus 3 to the power 4 annihilates all these functions here. So we have x e to the power 3x, x squared e to the power 3x, and then x cubed e to the power 3x. So we have one function that annihilates 4 different functions. So in general, we have more than one annihilator for a function. So d minus 3 is an annihilator for e to the power 3x, but d minus 3 to any higher power of d minus 3 will also annihilate e to the power 3x. Now, in general, we can annihilate the following functions. E to the power rx will be annihilated by d minus r. And then if we have a power of x in front of e to the power rx, then we can annihilate that by d minus r to the power k plus 1. So you need a power that's 1 higher than the power of x. And any power higher than this will also work. Now, if we look at cosine beta x or sine beta x, think that that corresponds with auxiliary root of plus or minus beta I, and the annihilator for that is d squared plus beta squared. So again, if you think of that in terms of the auxiliary equation, that gives you r squared plus beta squared equals 0, and then r squared equals negative beta squared. But because this is a negative number for any beta, you then get r equals plus or minus beta I as the solution there. So that's the annihilator for cosine or sine. And then again, if we have that x to the power k in front of a cosine or a sine, we get a similar behavior as we saw here. So we have an x to the power k here, an x to the power k here, and then our annihilator here becomes d minus alpha squared plus beta squared. And then we have to raise that to the power k plus 1. Because we have x to the power k here. We'll do some examples in the next video.